Hi everyone and welcome to this video. Last time we discussed about cellular automata and we have shown how to implement this in BASIC. We also have shown an example of a cellular automaton running on the MSX. So this time we are going to go in a different direction and we are going to introduce the Conway game of life. This is actually something that is pretty old, but this is a very interesting game and I'm going to explain how to implement this game in BASIC. Before we can do this, of course, I will introduce the rules for this game, and then I'm also going to introduce a generalization of the evolution rules, so to make things slightly more interesting. Everything will be implemented in BASIC, and of course at the end of this video I'm going to show some examples so that all of these start to make sense and is easy to understand. There is some useful links. So the first one is this one. If you are interested in duplicating the results that you are going to see here, this is the link to go. You are going to be able to download a QBasic compiler. I will put this link in the description below. But also there is a useful article if you want to understand the game of life made by Conway. So there is a Wikipedia article that is actually pretty interesting and very clear. Also, all of this is inspired from a previous demo that I have made a while ago. So I'm reporting here the link to this previous demo so that you can have a look at it and you will understand where we are going in this video. As always, I'm taking the chance to thank all of you. It's very nice to see that you continue to subscribe, you continue to leave comments. This is very encouraging, so thank you so much for continuing doing this. So what is this game of life coming from Conway? First of all, think of this as a big grid where you have cells and every cell can be in one of two states. They can be either white or they can be black, or let's say they can be empty or they can be filled, for example. So you have two states for every cell. And in practice, what you are doing every time you want to evolve the state of the cell, you want to give an update to the state of the cell. So the way you do it is actually pretty simple. You take the cell and you take the neighbors that you have around. So this is what I am showing here in this figure, where the central cell in blue is the cell we want to update, and the cells around, which are 8 and which every has a number assigned, these are the neighbors. And we are going to use actually the state of the neighbor to update the state of the central cell. The way we do it is actually quite simple to follow. It's made by following the 4 rules that you see here. So we have these 4 evolution rules. The first one says that any live cell with fewer than 2 live neighbors dies. So what do we mean by living and dying here? So you can think of the cells being black as living cell and the cells in white as dying cells, so cells that are dead. So if the cell is black, in practice, or let's say any cell that is black with fewer than 2 black neighbors practically dies. If we take the second rule is telling us that any black cell with 2 or 3 black neighbors continue to be black. The third rule is telling us that any black cell with more than 3 black neighbors dies, and so it becomes white. And eventually the last rules tell that any white cell with exactly 3 black neighbors become a live cell, so it becomes black itself. And these are practically the rules that you have to follow in order to implement the Conway game of life. So now I'm going to present a generalization of these rules so that we can make things slightly more sophisticated. There are many ways to generalize the Conway's game of life, so I'm proposing one here. It could be anything, it's just for the sake of making things different and more sophisticated. So far what we have seen is that the game of life consists of a grid of cells which can be practically in two states, and we use those states to evolve the grid in time. In here, what we do is we introduce this first generalization where rather than the cell being in one of two states, the cell now has a real value, and the real value can be something between, let's say, 0 and 1. Now your neighbors are still the same neighbors, but this time rather than taking colors, we are going to take the actual value that we have on the neighbors, and we are going to make the sum. And now that we have the sum, we can come up with some evolution rules that I am proposing here. So the first rule will say that if the sum is smaller than 2 or is bigger than 3, essentially you decrease the value of the central cell by some value, some amount equal to dv, and this is a fixed amount. Rule 2 is saying that if the sum is in the range 2 and 3, so if it is between 2 and 3, essentially you modify again the value of the central cell, but this time by increasing by an amount that is fixed, so by the amount dv. Rule 3 is saying that if the sum is bigger than 1, then the sum has to be set to 1, and rule 4 is saying that if the sum is more than 0, then the sum is equal to 0. By using these 4 different evolution rules, you come up with a completely different game, and we are going to run the original game of life. We are also going to run this generalization of the game of life, and we are going to see how things can be very, very different because of different evolution rules. We are now ready to go through the code. So the first thing I'm going to do is to show the list of the code so that you can stop it at any time and you can have a look at the details. Let's now go through some part of this program. The very first thing that we see here is the screen definition. This is not difficult to explain. And what you see here is that we define a screen definition because we want to go full screen. Then on this line here, we are practically deciding what is the set of rules we want to use. And in this particular case, we have two options, which are Conway or generalization. Then on this part here, what we are showing is, or what we are defining actually, is the dimensions of the grid. So this is practically the dimension of the grid that we are going to use for the game of life. And here we define the number of steps that we want to use during the evolution. So you can think of this as a number of steps. You can think of this as the number of iterations that you want to use to apply the evolution rules. Of course, we also have to specify initial conditions. In our case here, we have different ways to do this. For example, here you can see that we have different choices like random, glider, cell, or multiple gliders. I'm going to show these examples later on in this video. Of course, here we have to define, we have to allocate some memory for the current and, let's say, the future grid. So practically the game is made of a grid. We always want to keep the current values that are stored in the grid, and then on top of that we want to build the future grid that is going to be practically the updated grid. Then we reset a few arrays. So for example, here we reset the array consisted of the current grid. And then here, depending on what we have chosen in terms of, let's say, initial conditions and rules, we start to have initial conditions that are being implemented in the grid. So for example, if you choose the rules being Conway, and if you choose the initial conditions being random, what this part of the code is going to do is to go through every cell in the grid through these nested for loops here, and every time it's going to shoot a random number, and if the random number is smaller than 0.5, then the value of the cell in the grid is 0, otherwise it is 1. And in the same way here you can see if your rules are generalization, then now your cells can have any value between 0 and 1. So random here would mean an actual random number, not just 0 or 1, but a random number that can go from 0 to 1 in this case. And then in the very same way, I mean, you see other kind of initial conditions that are being implemented here. So if we choose the cell, for example, we are going to implement these kind of initial conditions. And this continues like that, for example, for the glider that you see here. So here we define the glider by hand. Or for a set of multiple gliders, same story here, we define every glider by hand. So this is glider number 1, glider number 2, glider number 3, number 4, and so on. So now here we get to the interesting part of the code, which is the evolution of the system. And of course, the evolution of the system is going to depend on what kind of rules we have selected at the beginning. But there are a few things that remain the same. So for example, at the beginning we plot the grid, so we want to know what is, or we want to visualize what is the current grid. So this is the way we do. We are going to call this subroutine here, and I'm going to show you what this subroutine does, but you practically already know. Then of course we store the values of the previous state of the grid, and we do it by practically updating the array prev underscore grid by practically storing every value of the previous grid, or which was the current grid in the previous iteration step. And now here we apply the let's say the rules to evolve your game. So depending on what rules one chooses, the evolution is going to be different. So what happens though is that every time what you are doing is you are checking your neighbors, and then you are applying the rules. And what you see here is that we are taking care of the boundary conditions. So for example, here we are taking care of the upper left corner, here we are taking care of the upper right corner, and here we are taking care of the lower left corner, and here the lower right corner. And as soon as we get out of the, let's say, corners, here we can apply upper boundaries and lower boundaries, but also left and right boundaries as well. And once we are done with all these boundaries, this is where we can take care of the internal domain, where we apply the rules that we have discussed just a while ago. If we go ahead with this code here, of course what you see here is that if we want to visualize things in a proper way, we can add some delay. The delay here is made through a for loop that is going to take some time, so that the visualization becomes comprehensible. If we now continue with the code, here this is the routine, this is the implementation of the routine that deals with the neighbors. So in practice what it does, it's going to compute the sum of the values of the neighbors, and the sum is going to be different depending on the rules that you have. So if you are taking care of, let's say, the classical rules of Conway game of life, this sum here is going to tell you how many black cells you have in the neighbors. And if you take the generalized rules, then things are different, because then this sum here is just going to be the sum of every value that is stored in every cell that you have in the set of neighbors. But practically these sums remain the same, it just depends on the value that is stored in the cell. And then once we have that, we can now go through the subroutine that implements the rules. So it applies the rules over the grid. And as you can see, if the rules selected are the Conway rules, practically we are applying the rules that we just discussed in the case of Conway's game of rules, so the original rules. And if we have selected the rules as being generalization, then you see here that the rules are slightly different, but these are the rules that we just explained earlier in the video. Eventually here we have a plot grid subroutine. This is easy to understand. What it does is practically, depending on the rules that you choose, it's going to show the value of the cells on the screen. So if we are in the presence of the original Conway game of rules, we are just going to have black and white cells. But if we are in the presence of generalized rules, essentially the colors now are going to provide what is the value that is stored in the cell. So I am now going to proceed with running a few examples. This is the final part of the video. So this concludes the video for today. As always, I want to thank you for your attention and for being here, and I hope to see you in the next one.